App number 3 kind of summarizes information from the two previous apps and gives an overview of the whole PCA model. You can see this model here. You can see a lot of numbers, but let's take it eventually, right? So this is the main PCA model formula. So you can see X, it's original data. You can see in this case I have only 5 points, and they are predefined. You cannot change them. So this is the original coordinates. For example, if I select this one, you can see that this coordinate has -1 for x1 and 2 for x2. And then you can see we reproduce these coordinates as a sum of other two matrices, right? This matrix gives you coordinates of the orange points, but these coordinates are in original space. Okay, it's not in the scores. It's not in the score space. And this matrix gives you a difference between these original coordinates and the orange ones. For example, you can see that in my orange matrix, all coordinates for x1 are identical to the original one, and all coordinates for x2 are equal to 0. So therefore, the difference for x1 is 0, and the difference for x2 it's the same as this one. Why? Because you can see my initial orientation of latent variable is exactly x2. So my principal component 1 now it's the same as x2, and that's why we have this result. Okay. You can also see the loading, and you can also see the scores. For example, you can see that this score is -1, this score is -2, and you can see why, right? It's by 2 smaller than the origin. Now, we get this matrix by multiplying t and pt. But first of all, let me demonstrate how to find the scores, right? So in order to demonstrate it, I click score here. And then I need to change the orientation of my latent variable. For example, I will take some nice numbers like this. Let me just even adjust it a little, like this. Okay. So let's look at this. So this is our point of interest. Original coordinates of this point is -2 and -1. You can also see it here, -2 and -1, right? The orientation of this latent variable is defined by loading vector. So this red line is a loading vector. And then you can see that the coordinates of the loading vector is 0.8 and -0.6. You can also see it here. And you can clearly see that it's a unit vector, because if you take 0.8 squared, it will be 0.64. If you take -0.6 squared, it will be 0.36. Together it will be 1, and square root of 1 is 1, right? Now, how we do the projection? We simply take a coordinate of every point and multiply to corresponding coordinate of P1 and take a sum. So for example, -2 times 0.8 will be -1.6. -1 times -0.6 will be +0.6. And then -1.6 plus 0.6 will be -1. And that's exactly what you see here. And then exactly, it means that the distance along this orange line from the origin to the projected point, it's -1. And then you can see it's the same distance as the loading vector. Likewise, for this point, you can see the original coordinates is -1 and 2. Again, how we do the projection, we take this coordinate, multiply it to the corresponding coordinate of loading vector. So it will give you -0.8. Then you take this, multiply it to this, it will be -1.2. -0.8 plus -1.2 gives you -2, and that's exactly the score. Yeah. So this is how we find scores. And then you can see that you can change orientation and see how score changes as well. So that's the overall idea. Okay. Now, let me get back to this nice orientation. It's not correct one, but it's nice because it gives you some nice numbers, so it's easy to explain. And then let me show you the full model again. So now we know how to get the score values, right? The idea is now we need to calculate coordinates of these orange points in the original space in x1 and x2, right? So for example, what will be the coordinate of this orange point? We know that it goes by -2 that far along the orange line. And we also know that the loading vector, you remember the loading vector, this one, has a coordinate of 1 and it's oriented in the opposite direction, right? So what we need to do to find coordinates of these points in the original space, we need to flip the loading vector, so multiply it to -1, and then we need to stretch it twice. So if we take 0.8, multiply it to -1 and stretch it twice, we will get the x1 coordinate of the orange point, right? It will be -1.6. If you flip -0.6 and then multiply to 2, stretch it twice, So we will get 1.2, and that's exactly, you can see the coordinates, right? So minus 1.6, and this should be 1.2 because I have only 2 decimals, so this is kind of rounding error, right? Minus 1.6, 1.2. And you can compute coordinates of every orange point like this, right? So for example, let's take this one. So you can see this is minus 0.6, minus 0.81. How? So we take our score, it's minus 1. So it tells that the orientation of this, it's the same as orientation of the loading, but flipped because it's minus 1, right? So you take 0.8 times minus 1, you will get minus 0.8. Again, I have some rounding error, right? And then you have minus 0.6 times minus 1, you have plus 0.6. So that's exactly the coordinates of the orange points. Now, because we know the coordinates of the orange points and the blue points, we also can compute the distances between these two coordinates. For example, distance between minus 1.6 and minus 1. This distance will be minus 0.6. And that's what you see here. So these values is simply a difference between this and this. And this value is simply this value. This one is simply a difference between this and this. So again, you can see the triangle, right? So this is the residual distance. How we can compute it? We need to take a difference between x1 coordinates of these 2 points. And then we need to take a difference between x2 coordinates of these 2 points. And then if necessary, if you square this and take a sum of these squared distances, then you will get a squared residual distance, which we computed also in the first step, right? So this is how PCA works. And then if you click fit, it makes the best orientation. It finds the best orientation of the latent variable that minimizes this sum of squared values in E. So that's the overall idea of PCA, right? So we need to find orientation of one or several latent variables if we work in more dimensional case to minimize a sum of squared values in matrix E. So we need to find the orientation of latent variables that explains the biggest spread of the data as close to X as possible. Okay. And now I recommend you to play a little bit yourself. For example, if you select this point, you can see the score is 2.72. Try to compute 2.72 yourself. So just click score. You have the coordinates of the loading vector. You have the original coordinates. Try to calculate this 2.72. And then likewise, take 2.72, multiply it with these two coordinates. So it means stretch this red vector, stretch it 2.72 times. And if you stretch it 2.72 times, the coordinates of the stretched vector will be the x1 coordinate of the orange point and x2 coordinate of the orange point, which you see here, right? So this is the x1 and this is x2 coordinates of the orange points, okay? And then you take a difference between these two.